Hello everyone. Today I'm going to be showing my Redstone computers. For a long while now, I've been very interested in Redstone computers. I find them really cool. I mean, I watched all those videos back in like 2011 where people were building Redstone computers out of dirt and whatnot. And I thought, gee, I would love to do that, but I'd never been able to figure it out. And you might have seen some of these contraptions off in the distance from my other video about my shulker farm. So I figured, hey, you know what? I've got them built. I might as well make a video out of them. So it's a long journey to build a Redstone computer because I wanted to start fresh. I wanted to build my own. I didn't want to go off of someone else's design. And so I I downloaded worlds. I um, examined how people's computers worked. It took me just a long time to figure out what I was doing. And so the first computer that I really ever built that was my own is this one here. And this one only runs on 4 bits. And the problem with 4 bits is that the biggest number that you can possibly use is 15. That's the biggest number supported by 4 bits. Although the output on this is 5 bits, so I guess the highest number is what, like 31, I think. Don't quote me on that. But I was so proud of myself when I made this, and I'm going to explain it a little bit here. I'll just show you how it works. So, programmed into this computer right now is what's called the Fibonacci sequence. And so I'll explain that. It's 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 2 equals 5, 5 plus 3 equals 8, 8 plus 5 equals 13, 13 plus 8 equals 21. It basically adds up the numbers and then adds the output to the original input. So, it just kind of flip flops. But if I show that off here, if I put in 1 and I add those together on this computer, you'll see it running down there. You'll see the clock ticking away, and you'll see on these buses, you'll see the numbers output. So 2, 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 2 equals 5. There we go, 5. 5 plus 3 equals 8, and so on. I'll stop it there. And I'll just run through a little bit how it works. So as you saw, I flicked that lever to input. So these come down over here. These red lines come over here, and they go into what are called registers. And the registers basically just save the number that you've inputted so into this little thing here. Oh, well, whatever. I'll fix that later. That it saves it in there, and so then it'll output these numbers. As you can see, it's outputting some numbers right now. It'll output these into the ALU, or I guess an easier term for it would be the CPU. And this CPU, I didn't do much with it. It just has an adder and a subtractor, which is something I'm not going to get into this video because that's a little too complicated. But as you can see, it inputs into the adder here, and then it outputs down here. But if we want to use that output, we have to save it somewhere. So we save the output in RAM over here, or random access memory. And we can call each different one of these. We can say load from RAM 3, 2, or 1. And so it will output up back here, run across these wires, and then back into here. So we can write a program to control this computer. And basically it just adds, saves, add, saves, add, saves, add, saves, and so on. And it will write it into RAM and then eventually display it on the screen. But you can only get so far with 4 or 5 bits. And you can only get so far with this, which is called the ROM, which is what is the program that controls the whole computer. And so I said, I want to be able to make a recursive program, a program that can run over and over again just based on a couple instructions that are saved in RAM. And so another component of a computer that can be quite useful other than, the CPU or the RAM is called a control unit, which is right here. And a control unit does exactly what it says. It reads operation codes or instructions out of RAM, decodes them, and then sends out instructions down these wires to the different components, like the clock or the registers. And so this computer is a bit more fancy than that one. It's still only 4-bit input, 5-bit output, and it's much slower because it runs out of RAM. But if I start it up here for you, you'll see what's going on here. So I have saved in RAM a program, and we can watch it turn on. It'll be out here actually. If you see how that wires on, that's decoding things. So right now, right just then, it was telling it to add, and now it's telling it to save. And now it's telling it to reset back to 0 because it's looping. It's looping, so it reset the clock back to 0. So now we'll go again. Okay, it says add and then save on that line. It'll add again, and then it'll say save on this line. Yep, save on that line, and then it'll reset so it can loop. Because I didn't want to write out a huge program, so I just have it all saved in there, and it just loops around. And how it does that is by implementing a control unit. But once again, you can only get so far with 4 bits. Highest number you can do is 15. And so originally I had the program all written into this ROM, or read-only memory, and I didn't want that. So if you want to make it, say, for example, 8 bits, this ROM would have to be really long in order to program that. So if we come back over here to where we started, this is my new 8-bit computer that I just built. And there are a couple other problems that come along with 8-bit computers, like dealing with the display. This has to decode a whole bunch of stuff because otherwise this thing would have to be gigantic to display all the numbers, because with 8 bits you can display up to 255, which is much bigger than 16 or 15. So as you can see, this computer just is basically double the width on the processing side. So there's the registers once again. The adder is that white stuff underneath there. The subtractor's that. And here's the RAM. As you can see, it's much bigger. The control unit didn't change at all. It's the same control unit, and same with these wires. But because I have the program written into RAM and it can run recursively, I didn't have to make this read-only memory way long to run the program up to, 255 or however big it goes. So once again, this computer runs the Fibonacci sequence. We'll wait for it all to reset. Okay, let's push the button one more time. There we go. And it's reset. So the display will go back to 0. Perfect. So we'll input 1 plus 1 into this computer, and we'll watch it go. Again, it's very slow because there's just so many repeaters and whatnot, and it just takes so long. So 1 plus 1 equals 2, and it will save it there, we saw. 2 plus 1 equals 3, and it will save it into the second register. And then it will reset on that gray line and restart the program over again. So 3 plus 2 equals 5, and we'll see it output on those red lines down there, and it will save it. And then 5 plus 3 equals 8. And I might speed this up a little for you here because it's going to take a while. Okay, and that is the last number right there, 233. So, oh, let me turn it off. Okay, yeah, and then it overflows because it's too big of a number. Anywho, yes, so because I ran it out of RAM and have it all programmed with different numbers and whatnot, it runs off a control unit and just works out so much better than having to build out a giant thing of RAM. Anyway, that's my 8-bit computer. I just wanted to show it off there. Thanks for watching.